For more than a century, black holes have represented the most absolute rule in physics. They are regions of space-time where gravity becomes so extreme that nothing escapes. Not matter, not information, not even light. A black hole is not defined by what it is, but by what it prevents. Once something crosses the event horizon, it is lost forever. This idea is not metaphorical, it is mathematical. It is built into the structure of general relativity itself. Darkness is not an expectation near a black hole, it is a requirement. And yet, in recent decades, that certainty has begun to fracture. When astronomers observe black holes, they never see the object directly. Instead, they see the universe reacting to it. Stars bend, light curves, dust disappears. Around many black holes, vast accretion disks form, violent rings of superheated matter spiraling inward. These disks shine brilliantly, not because the black hole emits light, but because matter is being torn apart just before vanishing. This distinction matters. The light is allowed only because it exists outside the event horizon. Relativistic jets follow the same rule. Twin beams of plasma erupt from the poles of some black holes, driven by extreme rotation and magnetic fields. These jets extend for thousands of light years, carrying enormous energy into space. They are spectacular, but they are not violations. They never originate from inside the black hole. The rule still holds. Until observation begins to complicate it. At the edge of the event horizon, instruments have recorded something unexpected, faint, localized, inconsistent. Light that does not behave like reflected starlight. Light that does not shear or spiral like accretion material. Light that appears to exist exactly where physics insists it should not. These emissions are weak. They do not illuminate space. They do not form beams or flares. They appear briefly, vanish, then sometimes return. They resist repetition. They sit at the boundary between detection and doubt. From one wavelength, nothing is seen. From another, something appears. The problem is not brightness. The problem is location. Classical physics predicts that the event horizon is a one-way surface. No radiation should originate there. Yet theoretical physics has long suggested something more subtle. According to quantum field theory, empty space is not truly empty. At microscopic scales, particle pairs constantly appear and annihilate. Near an event horizon, gravity may separate these pairs, allowing one to escape while the other falls inward. This process, known as Hawking radiation, implies that black holes may emit energy extremely faintly over unimaginable timescales. But Hawking radiation has never been directly observed. The emissions detected near black hole boundaries are not clear confirmations of this theory. They are stronger than expected, less predictable, not uniform. They do not behave like clean quantum leakage. They also do not behave like plasma, jets, or disk turbulence. They sit in between. As data accumulates, the contradictions deepen. Some black holes show hints of these emissions, others remain perfectly dark. Some observations detect anomalies, others see nothing at all. No single model explains all cases. This inconsistency is unsettling because physics depends on universality. If a rule is fundamental, it should apply everywhere. Instead, the universe appears selective. The conflict is not dramatic. There are no explosions, no cosmic warnings. The tension exists quietly at the edge of measurement. Instruments register signals that are too persistent to dismiss, but too fragile to confirm. At large scales, the universe remains stable. Galaxies rotate, gravity behaves, light follows predictable paths. The contradictions vanish when observation becomes precise, patient, narrow, and sustained. Only when observation becomes precise, patient, narrow, and sustained do the fractures appear. This raises a deeper question. What if black holes emitting light do not overthrow physics, but expose its limits? General relativity describes gravity with extraordinary accuracy. Quantum theory describes the microscopic world with equal success. But at the event horizon, these frameworks overlap and disagree. Neither fails completely, neither explains everything. The black hole does not announce this conflict. It does not emit answers. It only reveals that the boundary between what is known and what is assumed is thinner than expected. The light near a black hole does not shine. It whispers. It appears briefly. It disappears. It leaves behind uncertainty, not evidence. Perhaps black holes do emit light. Perhaps they always have. Perhaps it has simply been too faint, too conditional, too easily lost among louder phenomena. Or perhaps the contradiction is not in the universe at all, but in the way humans insist on complete explanations. The black hole remains what it has always been, silent, dominant, and indifferent. It does not resolve the debate, it sustains it. And in doing so, it reminds us of something fundamental. The universe does not promise clarity. It does not adjust itself to human understanding. It allows us to observe, nothing more. If you want to continue exploring the most unsettling, unsolved mysteries of science and ancient history, subscribe to the channel and join us in the next episode, The Ancient Stone Circles with No Known Purpose.